Hey guys, Kenna here. So last class we introduced you to the different ways that light behaves when it interacts with matter, and we focused on reflection. Today we're going to go ahead and move on, spend some more time on refraction as we go ahead and start looking at light as it bends going from one medium to another. So let's take a look at our essential questions. Number one, what is the index of refraction? This will be important when we get to the next one. What is Snell's law and how do we use it? So the index of refraction is going to tell you something about the medium so that we can go ahead and make a relationship as a light wave passes from one medium to another. Number three, explain total internal reflection and what the implication of this is. Now, when we start thinking about some examples of total internal reflection, we can start looking at like diamond sparkling, or we can go ahead and start looking at fiber optic cables, these types of things. Number four, what are the different types of lenses and how do they work with respect to a ray diagram? Okay, we're going to start looking at the process of light bending, and we're going to go ahead and look at how light bends going through a concave and convex lens. Next one, how do myopia and hyperopia work and what are the causes? These are the more proper terms when we go ahead and start looking at nearsightedness and farsightedness. And so we need to understand which is which and how are they caused? What does that look like in terms of the light rays in your eye? And lastly, we'll finish up by taking a look at rainbows, what forms them, and what makes diamonds sparkle. So let's review the four interactions we introduced you to last time. As we discussed last class, when light interacts with matter, four things can happen. The light can, one, go through almost unchanged, and this is what we call transparency. It can go through but scatter. This is what we call translucency. It can bounce off the material. This is called reflection. And it can transfer its energy to the material, and this is called absorption. Today we'll be focusing on light traveling through a substance, so we'll be looking at transparency and translucency. As we saw last class, light goes through some things, glass, water, eyeballs, air. However, light does not travel at the same speed through different materials. Refraction is caused by a change in the speed of a wave when it passes from one material to another. Now, there's a really simple demo that you can do in your own house. Go to the kitchen, get yourself a nice clear glass, and then go ahead and pour some water about 2/3 of the way up. Then take a pencil or a straw or something like that and go ahead and hold it above the glass as you go ahead and look at it from the side, right? Perfect side view. And then go ahead and put the pencil, straw, whatever it is, into the glass slowly and look and see what happens. Now, it won't look, if you have a nice round glass and you have a nice clear glass, it won't look like it goes straight in right away. It'll look like it's bent a little bit. And the reason for that is because of the changing of the speed of light as it goes from one material to another. If the light wave is traveling at an angle and that the speed of that light travels differently in two materials, the wave looks bent, or what we call refracted. Now, I don't know how many of you fish, but if you've ever been fishing or been to a lake or a river where there are fish swimming in it and you can see them pretty easily, when you perceive where that fish is, it turns out that that fish is actually deeper than that. Because what happens is the light rays coming off the fish get bent as those rays get bent going from the water into the air. Okay. And so we look at this changing of speed as it goes from one material to another, and we can calculate this pretty easily using Snell's law. But before we start using Snell's law, we need to understand what an index of refraction is. Now, an index of refraction is a property of the material and it indicates how much the speed of light is reduced. Okay. Now, the speed of light in a vacuum is going to be unimpeded. Okay. There's nothing slowing it down, so it's at its maximum speed. And so we're going to call that 1. Okay. Anything greater than that is going to cause a slowing down of the material, of the light through the material, I should say. So the presence of the material slows light's progress because of interactions with the electrical properties of the atoms that make it up. The larger the index of refraction, the more light is slowed down in the material. So you can calculate the index of refraction by the letter n. And n is equal to c, which is the speed of light in a vacuum, over v, which is the speed of light in the medium. And if you remember when we talked about this last unit, the speed of light in a vacuum is approximately 3 times 10 to the 8th meters per second. So just a minute, and you want to take a thought about why n is always going to be greater than 1. Okay, so pause the video here and think about why that is. Did you figure it out? So n always has to be greater than 1 because if you look at our index of refraction, it's equal to c over v. And c, remember, is the speed of light in a vacuum. And that's the speed limit for the universe. So our top number is always going to be greater than the number on the bottom because all mediums are slower than a vacuum. And therefore, light is always going to slow down from that speed of 3 times 10 to the 8th meters per second. So let's start by doing a little bit of practice. So what is the speed of light in quartz? We'll tell you that quartz has an n, okay, n is, remember, the index of refraction, 1.52, and the speed of light in a vacuum is 3 times 10 to the 8th meters per second. So pause the video here and then go ahead and do the math and calculate this out. Okay, so let's go ahead and work this out together. See if we got the same thing. So we'll start by taking a look at the equation. So remember, n, which is our index of refraction, is equal to c, the speed of light, over v. And that's the speed in the other medium. So if we take the speed of light, we're looking for the speed of light in quartz. We take n, which is equal to 1.52, and that's going to be equal to c, 3 times 10 to the 8th meters per second, over v. Now, I will point out that n does not have any units. And so in order for n to have no units, the velocity of the light as it goes through the medium, in this case quartz, has to have the same units as the speed of light in the vacuum. So this will be in meters per second. So if we want to solve, we can switch these two variables and we get v is equal to 3 times 10 to the 8th meters per second over 1.52. And you can just go ahead and plug that in your calculator. And what we end up with is the velocity is equal to 1.97 times 10 to the 8th meters per second. Let's see if that's what I got the other day. Hey, look at that, 1.97 times 10 to the 8th meters per second. Excellent. Okay. All right, so hopefully you got that and you understand the relationship between the speed of light in a vacuum and what the index of refraction tells us. All right. Okay, so if we go ahead and take this understanding, we then can go ahead and begin to look at looking at different materials and what their speed of index of refraction is. Now, the index of refraction essentially shows how much slower light travels than in a vacuum. Glass, for example, has an n value of 1.52, meaning that light travels about 1.5 times slower in glass than it does in a vacuum. Water has an n value of 1.3. Air, which is what we get our light through, is 1.00028, so it's pretty close to 1. The air molecules do slow it down, but compared to a vacuum, compared to these other n values, it's pretty low. Ethanol is 1.36. Quartz, as we just solved, is 1.52. Notice that quartz and glass are very similar. And then in a vacuum, n equals 1. And this is because the speed of light is at its full capacity. This understanding allows us to go ahead and calculate using Snell's law. Now, this is probably one of the more important equations that you'll use in second semester. So please make sure you make note of this. Okay. Notice we have N1. So this is going to represent the index of refraction for the first material. Okay. And then here, N2 is going to be the index of refraction for the second material. And then these thetas here, theta 1 and theta 2, represent the angle off the normal. So remember, the normal is going to be right here. The normal is perpendicular. Okay, so remember, perpendicular to the axes, or the barrier between the two mediums. So up here we have medium 1, and down here we have medium 2. Okay, so here's theta 1, and here's theta 2. So Snell's law is the formula that we're going to use to describe the relationship between the angles of incidence, theta 1, and the angle of refraction, theta 2, when referring to light or other EM waves passing through a boundary between two different isotropic media, such as water to glass, or glass to air, or something along those lines. Now, it's important to notice that we use this term isotropic. If you remember that prefix iso, iso means the same, and so the material needs to be made of the same thing all the way through. If you get different pockets of different things or different densities, these types of things, the calculations are going to be doable, but much more difficult. And you would have to know where the pockets were, what their different n values were, depending on where the pockets are and how big they are and how long that's going to last. And then you can start doing the same thing, but it's just more complicated version of what it is that we're looking at. Okay, so let's go ahead and try some Snell's law. So Snell's law, again, is that relationship between the angle of incidence and the angle of refraction based on the index of refraction for both of the materials represented in the equation here, where N1 is going to be the index of refraction for the incident material, angle of degrees in initial one, or incident material. This is the index of refraction for the refractive material. And then we have the angle of refraction, again in degrees, please not do this in radians, for the second material. And again, that's with respect to the normal. Okay, remember that's perpendicular to the barrier. All right, so try drawing the ray diagram first. As with everything this year, try and visualize what's happening. If your angles are off, it's okay. You're going to do the math, but at least get an idea of what's happening. So what is the angle of refraction when a ray from air with the angle of incidence of 25 degrees is incident to water? Draw the ray diagram. So I'm going to let you go ahead and try this, but before you do, let's go ahead and write down what we have and do our diagram. So here's our barrier. Okay, we're going to be starting with air. So this is going to be air, and we're going to be going into water. The light ray is going to come in at an angle. Okay, here's your normal. This angle here is theta 1. This is going to be the 25 degrees that we just talked about. And then we're going to go ahead and come off out this way. This is going to be theta 2. And this is the one that we're trying to solve. And we know that we have the index of refraction for both air and for water. So I can write those here too. And n value equals 1.33. Okay, so if you remember our equation, okay, we've got n1 sine theta 1 equals n2 sine theta 2. And we've been given most of these things. So this is going to be 1.00028 sine 25 degrees equals 1.33 sine theta 2. And that's what we're going to be solving for, is theta 2. Okay. So then we go ahead and simply do the math. All right. inverse sine, and we end up with a theta 2 of 18.5 degrees. All right, let's double check our work, see if it's what I got last night, and there you have it. Okay, so there is the process by which you go ahead and use Snell's law to go ahead and calculate the um, angle of incidence or angle of refraction, I guess I should say. Okay, all right. So the next example that I want to highlight for you is total internal reflection. This can occur when the ray goes from a higher N into a lower N material. Above a critical angle, the angle of incidence, the ray is reflected and does not refract. So instead of bending, it just bounces back inward. For problems like this, you need to go ahead and set the angle of refraction to 90 degrees and solve for the critical angle. Let's take a look at what that looks like. So in this particular instance, going from water into air, you'll notice that when we have 45, when we go ahead and have 48, we're still going above the horizontal. But when you go ahead and get to a critical angle, in this case 49 degrees, which is the initial, your second angle will be 90. You can find out what the critical angle will be by using this. And anything beyond that critical angle will give you total internal reflection, and no actual light will be bent outward from the material. Okay, so again, the angle at which light begins reflecting back into a reflective material is known as the critical angle, and it depends on the index of refraction. And for water, as you can see in this example, the critical angle is about 49 degrees. Now, depending on the composition of the water, if there's salts in it, other particulates, that might not be exactly true, but you get the idea. So let's go ahead and do a sample problem so you can see how this works. In this case, we're going to find the critical angle. So again, if you're thinking critical angle, you should be thinking about 90 degrees. Okay, it's critical angle. We're going to write 90 degrees just to remind ourselves for a light ray that is incident from water to air. Okay, so let's do our drawing. So we're going to have a light ray coming up and then coming out. Here is our normal. Okay, this is our incident, our theta 1. And this one, if we're going to look for a critical angle, isn't going to come out, but is actually going to go ahead and end up going straight across. Okay, so coming out this way. And so that's going to be our theta 2, which is equal to 90 degrees. And we have from water into air. So same equation. Equation hasn't changed. N1 sine theta 1 equals N2 sine theta 2. And then in this case, we know that our theta 2 is 90 degrees. So we have our N that we're starting at, which is 1.33 for water. We're trying to find that sine theta 1. What is that critical angle? Equals air, 1.00028, and sine theta 2, sine 90 degrees. Okay. Now, if you remember your SOHCAHTOA stuff, we should hopefully remember that the sine of 90 degrees is 1. And so we don't even hopefully have to put this into the calculator, but 1 times 1.00028 is going to still equal 1.00028, and that's going to be divided by 1.33. Okay. Okay. And that gives us 0.75, and then we do the inverse sine of that. So sine theta 1 equals 0.752, and then we inverse sine. Inverse sine of a sine gets rid of it. So then we're end up with theta 1 is equal to, and that equals 48 8.8 degrees. And let's double check our work. Last night, what did I get? 48.8 degrees. And so there you have it. So that's how you go ahead and do your critical angle when you're talking about total internal reflection. Okay. All right. Now, when we go ahead and start looking at this whole process, this is going to change a little bit depending on when we're dealing with a convex and concave material, because you have to think about how long is it in the material for. So when we're starting to look at lenses, if it's thicker in the center versus the edges, it's going to slow down or speed up through that material for a longer or shorter period of time. When you're looking at a concave, it's thinner in the middle and it's thicker on the outside edges. So those light rays that travel through the thicker parts are going to be affected more by this refraction. Remember from last time's notes that when we go ahead and take a look at concave and convex, it's important to go ahead and remember that a concave is one that you can walk into, okay? And convex then is going to be the one that bows out towards you. So if you're coming at it from this direction, concave you go in, concave. When you can't and it bulges out, this is convex. And so it's just important to keep those. And again, you can have like this example right here. This is planar convex versus a double convex. This is a double concave versus a planar concave. And so there are different types of lenses that we can use. For most of what we're going to be doing in this course, we will use the double convex and the double concave. Okay. All right. Now, convex lenses are lenses that converge light rays that help bring them together, because those rays that are at the top portion are going to be bent differently than those that are more direct. And again, this depends on angle of incidence versus angle of refraction. So we could use Snell's law to go ahead and dictate this. And again, if you want to see a little bit more of this, the lens simulation at simbucket.com/lenses and mirrors is a great place to go ahead and play with this. All right. Concave lenses are on the other end. So if a convex lens is a converging lens, a concave lens is a diverging lens, making the lens light rays go outward. So what you'll typically see is that the print gets smaller, unlike what we saw with the convex lens where the print got bigger. So plane mirrors, convex mirrors, diverging lenses can never really produce a real image. So this image is not what we would consider to be a real image. A concave mirror and a converging lens will only produce a real image if the object is located beyond the focal point. And so we'll hopefully get to see that when you go ahead and do your ray tracing diagrams. Now let's try and apply this to your actual eyeballs. Okay. How do you see? Well, your eyes are an orb and it has the opening portion, which is the pupil that's allowing light in towards the back of the eye. And we talked about the anatomy and physiology of the eye, where you have the cones and rods, the back of the eye, part of the retina that actually absorb the information. If an individual is nearsighted, that means the eyeball is too long and the image focuses in front of the retina instead of on the retina. So nearsightedness can be corrected using concave lenses to expand the focal length. However, if you're farsighted, the eyeball is too short, and so the image actually focuses behind the retina. Farsightedness can be corrected by a convex lens, which shortens the focal length to go ahead and place the image on the retina. Okay, so with normal vision, the light rays converge at a point that is right on the retina, so you get a nice clear image. But if you have hyperopia, you'll notice that the image focuses behind the retina, and we use a convex lens to go ahead and shorten where the rays are converging, and so that it lands on the retina. If you have myopia, you're going to correct that by using a concave lens, and that's because the image is falling in front of the retina, and we want to move it backwards so that the rays are actually converging on the retina. All right. Um, this is also a similar technology we use when we go ahead and create cameras. We use lenses to go ahead and help us get images. If you've ever seen a pinhole camera, maybe you did this when you were in elementary or middle school, I'm not sure. The hole is so small that the light hitting any particular point on the film plane must have come from a particular direction outside the camera. And so you end up getting an image that is produced that is actually inverted from what you're seeing. Now, in a camera with a lens, right, when you take pictures, even with your phone, the same thing applies. A point on the film plane more or less corresponds to a direction outside the camera, and the lenses have the important advantage of collecting more light than the pinhole does. But again, you see an image that is actually inverted from what you think you see when it's outside of that. All right, so let's talk a little bit about prisms, and then we'll go ahead and move on a little bit to looking at rainbows and diamonds. But we want to get the idea of if refraction is occurring, according to Snell's law, which it is, then why do we see the breaking out of colors when we go ahead and look at a prism? All right. Well, remember that white light is actually made up of a whole bunch of different wavelengths. And those wavelengths are frequencies that represent the electromagnetic spectrum in terms of visible light, which we think of as the rainbow. So this is Roy G. Biv. Okay, and if you're not familiar with that, I would encourage you to go ahead and make sure that you remember that the colors of the rainbow are Roy G. Biv. And this is from the longest wavelength to the shortest wavelength. Okay, this is the lowest, and I'll go ahead and put wavelength, lowest frequency to the highest frequency. All right, and again, remember that this is actually visible light, and that if we were to put this into the spectrum as a whole, the next thing you're going to find on this end is ultraviolet, and the next on this side you'll find is the infrared. Okay. Wavelengths of visible light range from the longer red waves to the shorter violet waves. White light, such as sunlight, is made up of the whole range, and when white light passes through the prism, the triangular prism refracts the light twice. Once when it enters the prism, and again when it leaves the air and re-enters the air. Now, because of this, what we end up seeing is that they don't bend the same amount. Because the longer wavelength light are refracted less than the shorter wavelengths are, red light is bent the least. And as a result of these different amounts of bending, the different colors actually are separated when they come out of the prism. This is the same basic concept that occurs when we deal with a rainbow. Rain droplets also reflect light. Okay. So when light enters near the side of a raindrop, much of that light is internally reflected. Remember total internal reflection? We can calculate that with Snell's law too. This is how a rainbow is formed. The refraction of the different wavelengths can cause white light from the sun to actually separate out into individual colors of visible light. Okay. Now in rainbows, the human eye usually can distinguish between only about 7 colors. And in order of decreasing wavelength, we go from red, orange, yellow, green, blue, indigo, violet, Roy G. Biv that we talked about just a minute ago. Now, when you look at an actual picture of a rainbow, it's valuable for you to kind of think about, well, where do the colors form and why do they form that way? And I have a short video that's actually going to go over that so you can better understand how rainbows form and why the colors fall where they do. Okay, enjoy the video.
Surely you've seen a rainbow. Maybe you were chasing tornadoes and happened upon one. But did you ever notice that the sky is darker above a rainbow than below? I never did until someone pointed it out. We're gonna find out why this is so with the help of refraction of light, dispersion, and the incomplete story you're usually told about why rainbows form. This story starts with refraction, the bending of light as it moves from one medium, like air, to another medium, like water, at an angle. Light actually slows down in water. Visible light would take 11 minutes instead of the usual 8 to get from the sun to the earth if there were a giant ocean in between. So as light slows down when it enters water, the beam is forced to turn. But unlike the constant speed of light in a vacuum, the speed of light in water depends on the color. Violet light moves slower in water than red light, so it will bend more as it enters the water. An incoming beam of white light will be spread out and separated into a spectrum of color. We call this dispersion. Now let's take this white light beam and send it through a droplet of water. Some of the light will refract into the droplet, then reflect off the back and refract back out to travel down to your eye, typically at an angle of 42 degrees between the incoming light and the outgoing light. This can occur in a circle of droplets, so if the ground weren't in the way, rainbows would be a full circle. Here's the fun part. Violet light refracts more in the water droplet than red light, as we discussed, so violet light should end up exiting higher in the water droplet than red. But if we look in the sky, red light is clearly higher than violet light. What's going on? Well, if you're observing from down here, this water droplet will only send red light to your eyes, and the violet light will pass above you. It's the droplets down here that send violet light to you, and the violet light will appear to be coming from lower in the sky, as it does. And that's how we get our colors in the rainbow from rain and sun. End of story. But there's one part I never understood. Why should all of the light enter the water droplet right at this point? Well, the answer is it doesn't. Some red rays enter here, some enter here, and they all exit in different directions. If we add back in the other colors, you end up with an exiting, jumbled mess of color. This mess of color should look white, but it definitely doesn't. So what's going on? This is where it gets more complicated than you usually hear. As this red light ray enters higher from the midpoint, it exits at an increasingly large angle. But watch what happens here. Eventually the ray turns around. No matter where red light enters the droplet, it can't go past this angle. That's the maximum angle, and it's 42 degrees for red light. It's slightly less for orange and yellow and so on until you reach violet, where the max angle is 40 degrees. So it turns out that at that maximum angle, you also get a maximum brightness. So even though all the colors can reach here around violet's max angle, because their maximum is beyond that, violet is at its maximum brightness, so it stands out against the other colors. Same goes for the max of the other colors. Below violet, no colors are at a maximum, so all the colors mix again and form white. That's why the sky appears lighter below the rainbow than above. None of the light can make it out above red, so the sky appears darker. Then how did this second rainbow sneak up there? Well, you'll notice the colors are flipped in order, and again that the sky is lighter above them. That indicates that the light had to reflect twice inside the droplet. In order to get the right angle down to your eye, it actually had to enter the droplet from below the midpoint, and you get a double reflection, causing a second rainbow. Now the story is complete. The end.
So as you can see there, it's a little bit more tricky when you start looking at rainbows than you may have originally thought or even been told in middle school. The last thing I wanted to leave you with is diamonds. Now, diamonds are unique because they have an incredibly high index of refraction. Their N value is 2.41. And they also have what's known as a coefficient of dispersion, a COD, of 0.044. So what does that mean? It means when light reaches a boundary, it can refract or reflect. And this is what creates the brilliance of diamonds based on what we call the 4 C's: carat, cut, color, and clarity. And depending on how they cut the diamond, if you do a princess cut versus a different type of cut, it's going to change the number of surfaces, which is going to change the amount of bouncing that occurs within the actual diamond to give you that shine or brilliance that's going to determine how much light bounces around inside the diamond before it's able to come back out again. So let's watch this last little video going over diamond clarity, and we'll call it for today.
When you're looking to buy a diamond, you'll notice that the clarity has a large impact on the price and may or may not make a difference to the appearance of the stone to the naked eye. The Clarity is a measurement of the amount of impurities and imperfections trapped within the diamond when it was formed over 1 billion years ago. The clarity grade is given to the diamond by assessing the quantity, type, and position of inclusions within the stone. The clarity grades are assessed at 10 times magnification. The highest clarity grade is flawless, and this means that there are no impurities in the diamond visible at 10 times magnification. Next down the scale is Vs1 and Vs2. VVS stands for very, very small, and at this level the impurities will resemble 5 to 10 microscopic specks of dust within the stone. This level of clarity is very rare, and you certainly can't see the impurities with the naked eye. The next step on the scale is Vs1 and Vs2, where Vs stands for very small. Here, the size and quantity of inclusions are getting more prevalent, although they're still not visible to the naked eye in a round brilliant cut diamond. Vs2 is probably the most popular level of clarity, as it's often a good balance between the appearance of the inclusions and its price. It also tends to be good psychologically, as you'll know that the inclusions in your diamond are very small and insignificant. Next after the Vs level is Si1 and Si2. Si stands for small inclusions. Here is a classic Si1 clarity. This particular diamond contains a feather, which is a type of inclusion, and is the main reason that this stone has been classified as an Si1. This is in fact quite a typical Si1 clarity. The inclusion is positioned just off what's known as the table of the diamond, which makes it less visible to the eye. Next is Si2. This is the level where the inclusions are getting quite a lot larger and more obvious, and then can sometimes be seen with the naked eye. In fact, I'd estimate that around 30 to 40% of the inclusions of an Si2 clarity diamond are visible. There are quite a lot of differences between individual diamonds which are graded at this level. It's therefore important to check the diamond from the side, as often the inclusion from above may be obscured by the facets in the crown, whereas from the side the inclusion could be easily visible. This does mean that it's important that the diamond has to be checked fully prior to purchase. Beyond Si2 are the levels known as PK1, PK2 and PK3. In the American terminology, these are also known as I1, I2 and I3. These diamonds do have obvious flaws when viewed carefully and are considered typical commercial quality. So this means that most of the uncertified diamonds that, for example, you might find on the high street will be somewhere between a PK1 and PK2 level.
So, not that you're running out to go ahead and buy diamond rings for anybody anytime soon, but hopefully you get an idea of how the inclusions are going to change in terms of pockets with respect to Snell's law. So the fewer inclusions you have, the more sparkle you're going to get out of your diamond, because you're going to have more uniform bouncing of the light internal to the diamond with respect to especially something like a princess cut. Okay, so diamonds, rainbows, all of these things get their appeal from light refraction, which is the bending of light, and it bends as the light transfers from one medium into another medium based on their index of refraction, which can be calculated by Snell's law. All right, guys, that's all I've got for you today. Stay healthy, stay safe, and I'll see you soon. Take care of yourselves. So long.